Hello everyone, here we'll be discussing chapter 4.2, which is a discussion on the mean value theorem. And there are not really too many theorems in this section. There are some consequences I guess we could possibly talk about, but the main two theorems are Rolle's theorem and the mean value theorem, or MVT for short. And they're basically the same theorem. In fact, one can say the mean value theorem is just a particular instance of Rolle's theorem to some extent, or kind of like a generalization thereof. But anyways, let's get to it and see if we can figure out what's going on. So Rolle's theorem says let f be such that these three criteria are satisfied, mainly that f is continuous on a closed interval a to b, differentiable on an open interval a to b, and f of a is equal to f of b. Now what these two mean is that, well, there are no breaks in the function from a to b as f goes from a to b, and differentiable, remember, means that its derivative exists everywhere, so there's no sharp edges. So just to kind of draw a picture for you, let's imagine this is A and this is B. The graph will look something like this. But actually, more importantly, we just care about the line segment from A to B, and that f of A is equal to f of B, so that mainly they have, again, the same y value. So imagine this is f of A and f of B. That's the y value that they both share. Okay. So now, what this is saying is that if these three things are met, so again, continuous, no breaks in the function, differentiable, so smooth, no sharp edges, and they both have the same y value, so the endpoints of that segment contain the same y value, then there is a number in between such that f prime of c is 0. A number c, somewhere in between, such that f prime of c is 0. And that actually happens here, and kind of here for this particular graph that I drew. So we have these kind of two C values, but I'm just going to call this one C. In fact, this one's probably not as obvious, so maybe I'll just draw one just to show you. But as it turns out, this always happens, and the more you think about it, the more this ought to be the case. In fact, really the only three scenarios, well, the only, I guess, weird scenario would be if f is just a straight horizontal line, because there it's not really curvy at all. It technically is differentiable and continuous on all of these values, and the y values are the same at the endpoints. But notice, since it's a horizontal, its derivative is 0 anywhere because it's a constant. So that, I think, makes sense. Horizontal lines have slope 0, so its derivative is going to be 0 everywhere. So that makes sense. But of course, if it's smooth like this, well, think of it like this. If you're connecting two points together with a curve, and it's a continuous curve, and it bends somewhere, if it goes up, then it has to bend back down to get to this point. And similarly, if it goes down, it has to bend back up to get to this point. Regardless, if it bends down, it achieves a maximum somewhere, hence the derivative will be 0 at that particular point. Similarly, if it goes down and bends back up, just like here, then we see there has to be a horizontal tangent line somewhere. So that's, I think, a visual proof, kind of hand-wavy, but that I think does the trick. The mean value theorem is a little harder to prove, but it's actually not that bad, and it's a consequence of Rolle's theorem. So here we say let f be such that these two are satisfied, which, by the way, are just the same first two for Rolle's theorem. Then there's a c in the interval a to b such that f prime of c is not 0, but f of b minus f of a all over b minus a, so that should be an a. But now let's recall, what is this? What is f of b minus f of a over b minus a? This should look familiar. This is just the slope of the secant line. So here I'm going to draw an image for the mean value theorem, similarly how I did to Rolle's theorem. And for Rolle's theorem, obviously I made it so that the endpoints have the same y value, but for mean value theorem, it's not necessarily the case. So in fact, no, I'm going to do it like this actually. Instead of making a curve in between, I'm just going to do like some arc like that. So clearly f of a is larger than f of b in this case. And in fact, look, if you were to connect these 2 points, this would be the secant line. And the slope of the secant line is precisely this. So what mean value theorem basically is saying is that there's some point c in between, some x value, c, in between a and b, that when projected to the function f, the slope of the tangent line at that point will be parallel to the secant line. Because of course to be parallel means the slopes are equivalent. Also, there's another way you can write this. If you multiply both sides by b minus a, you end up getting f of b minus f of a minus f of a is equal to f prime of c times b minus a. So that's another way of writing this consequence, but notice it's the same. In fact, this is better, in my opinion, because it just says there's some point in between whose secant line, or whose tangent line, I guess, is parallel to the secant line between these points. And why or how is this a consequence of Rolle's theorem? Well, if you actually tilt your axes, so I'm going to draw this in dotted red just because I don't have any other colors at the moment. So imagine this is our new x-axis and this is our new tilted y-axis. And I'm drawing it so that it's parallel to these lines. We exactly get Rolle's theorem. Because if you tilt your axis, x-axis and y-axis, then these 2 points will have the same tilted y value. So really it's just a kind of generalization if you were to kind of tilt things. So since it's true on the tilted axis because of Rolle's theorem, then it must be true here. Which sounds a little weird, but basically if you tilt your head, it's just Rolle's theorem. Anyway, so now we're going to see some consequences of the mean value theorem and Rolle's theorem. And particularly, we're going to focus on the mean value theorem, hence the name of the section. And it's kind of hard for me to say because the applications of these theorems aren't the greatest, but we'll kind of see they're pretty useful here and there. So let's take a look at those instances where they are useful, obviously, and see where it goes from there. So let me just say before we actually begin these examples here, is that polynomials are fantastic functions, especially when it comes to the hypothesis we saw for the mean value theorem and for Rolle's theorem as well. Because polynomials are continuous everywhere, their domain is even negative infinity to infinity, and of course they're differentiable everywhere because notice, if you take a derivative of a polynomial, you'll just get a polynomial again because of the power rule. So there's no sharp edges anywhere in a polynomial, it's all smooth sailings kind of. So now for this example here, it's asking us to prove that this equation x cubed plus x minus 1 equals 0 has exactly one real solution. So I'm going to start a proof here, but I'm not going to write too much detail. In fact, I didn't even leave too much space. But let me just say that the intermediate value theorem implies that there at least exists a solution. So there is at least one real solution. In fact, well, I'll just write that. There exists at least one solution. One real solution. In fact, we can even do better than the intermediate value theorem because that you need to actually find values to plug in and will give you negative and positive, which isn't too bad because notice if we call this function f of x, then notice f of 0 is negative 1 and f of 1 would be 1 cubed plus 1, which is 2 minus 1, which is 1. So actually there is a 0 in between 0 and 1 because 1 gives you negative, 1 gives you positive, so it has to pass through the x-axis somewhere by intermediate value theorem. But since it's a cubic, the equation looks something like that kind of. It does that kind of wavy thing. So it has to pass through the x-axis somewhere. So we know there's at least one real solution, but I guess what we're going to do is we're going to try to apply Rolle's theorem. So let's just say if there were two solutions, so let's say if f of a equals f of b equals 0 for a not equal to b, so this just means there are two different solutions, real solutions, then there exists, let me just say there is, in number c, in the interval a to b, such that f prime of c equals 0, and this is by Rolle's theorem. Now how do I know this? Well, remember for Rolle's theorem there are three requirements, and polynomials always satisfy being continuous on any interval and being differentiable in any interval, as we previously mentioned. But now we actually have two values that are suitable for an interval here, a and b, because f of a and f of b are equal to 0, they're equal to the same y value. This is exactly the third requirement for Rolle's theorem, that they have the same height basically at the endpoints of an interval. But of course, we need to find the derivative of f now, and you'll see that's where this kind of whole assumption here falls apart, or the hope of this falls apart. So when you find the derivative of f, you will get 3x squared plus 1. And no matter what you plug into x for this derivative, negative or positive or even 0, this will always be a positive value. And it's because you have a square plus a number. So this is all positive. So that implies that f prime of x is never equal to 0, so c doesn't actually exist. So what that tells you is that there's no way you can have two zeros of f. So this implies that f of x only has one 0. That completes the proof, because that implies that the equation only has one root, or solution in this case. But solution and root mean the same thing, so that's fine. So I hope that wasn't too hard to follow. I didn't draw a picture or anything, but if you wanted a picture, if this is the x-axis, and this is the function, cubics again kind of look like this, we're kind of assuming that a and b are these two x values, or we have these two zeros, and if that's the case, then by Rolle's theorem, there exists some point in between that gives you a horizontal tangent line, but the derivative of this function in particular is always positive, so that line never exists. So that means a and b can't actually give you the same x, or the same y value, I should say. Awesome. So now, this example is a little more specific. It tells you what to do, basically. And it says, find c in the interval 0 to 2, satisfying the mean value theorem for this function. So, well, remember that the mean value theorem really says what? I mean, the conclusion of the mean value theorem says that f prime of c is equal to f of b minus f of a over b minus a. So let me just say the mean value theorem implies this. And specifically, if we're looking at the interval 0 to 2, then that means the closed interval that this function is continuous on is a closed interval 0 to 2. So we're going to take b to be 2 and a to be 0 like this. So let's plug things in. We have an actual function, so we can figure what these values are. So f of 2 is 2 cubed minus 2, so it's 8 minus 2, which is 6. Notice f of 0 is just 0, and 2 minus 0 on the bottom is, of course, that, just 2. So we get 3. So f prime of c is equal to 3, but we know what f is again, right? We know f is this, and with that being said, we know f prime of x is 3x squared minus 1, kind of contrary to what we got here, 3x squared plus 1, but that's coincidence. And here we have f prime of c, so that's just plugging c in for x. So that means that f prime of c is, well, 3c squared minus 1 equals 3. So we're almost done. All we have to do really is just solve for c in this case. And I think we'll actually get two values, it looks like, but we need to check that both of them are in the interval. At least one of them will be. So let's see. If we add 1 to the other side, we get 4. And then we'll have to divide by 3. And then we'll square root. So that means c squared is equal to 4 over 3. And that implies by square rooting that c is equal to plus or minus the square root of 4/3. If you want to rationalize this, you totally can. But now it's up to us to check that both of these are in the interval 0 to 2. And clearly the negative one is not. Is the positive one? It better be. In fact, it totally is, because notice 4/3 is less than 2. It's 1 point something. In fact, it's 1 1/3. And the square root of something less than 2 is going to be less than 2. So this number is definitely going to be positive and less than 2. So in fact, the positive one is the one we're going for here. So the c value we really want is this. If you want to rationalize it, in fact, notice that the square root of 4 on top is just 2. So it's 2 over radical 3, or again, if you want to rationalize, that's 2 radical 3 over 3 if you multiply top and bottom by radical 3. So I'm just going to leave it like that and call it a day there. And now we'll move on to some more examples where we see some more results of these theorems. Right, so for this next example, it's kind of theoretical in some sense. Notice we get some certain properties of f of x Doesn't even tell us what f of x actually is. There's no formula or expression for it. So let's just read. It says, suppose f of 0 is negative 3 and f prime of x is less than or equal to 5 for all x. In fact, this statement basically, by the way, says that f prime of x exists for all values of x. So that's something to consider, because if it's less than 5 for all values of x, then that means it must exist for all values of x. Unless, of course, f prime of x is negative infinity or something like that for some value of x, but I'm not going to go there. That can be a little weird. Anyways, the question asks, how large can f of 2 possibly be? So let's see. We have f of 0 and we have f of 2. So for f of x, we want to kind of consider the mean value theorem on the interval 0 to 2. So what I'm going to do here is I'm going to say the mean value theorem implies that there's a c such that f prime of c is equal to f of b minus f of a. But again, kind of just coincidentally like the previous problem, b and a are 0 and 2 in this case. Those are the only x values we have here. F of 2 we know nothing about. F of 0 we know is negative 3. So in fact, notice this is going to be f of 2 plus 3 because it's minus negative 3, it's positive 3 all over 2. And this is again equal to f prime of c. So let me just write this kind of backwards. So there exists a c, and how we know this again is because f of x is continuous and differentiable for all values of x. How do I know that? Well, at least for all values of x in between 0 and 2, because for all values of x, f prime of x is less than or equal to 5. So that again implies that f is differentiable for all values of x. And if it's differentiable, then it has to be continuous, of course. Which is something we haven't spoken about too much, but that is a fact, actually. And so essentially the mean value theorem applies. So we can do this. But now notice f prime of c is f prime of, well, something. And this is f prime of anything is less than 5. So this has to be less than or equal to 5. So this gives us an idea as far as how large f of 2 can possibly be. It may be smaller than what we say it is, but the largest it can be is whatever we get here. So notice that we now have this equation, or I guess inequality really. F of 2 plus 3 over 2 is less than or equal to 5. Multiplying by 2, we get f of 2 plus 3 is less than or equal to 10. And then finally subtracting 3, we get f prime of 2 is at most 7. So the largest it can possibly be is 7. Awesome. That was kind of a weird problem, but again, mean value theorem and Rolle's theorem are kind of used to solve these weird problems where it's not obvious that you would apply it, but you definitely can. Now here we have these kind of consequences that are kind of the last thing we're going to be talking about, kind of. We'll still look at some other examples beyond this, but still, these are the last theorems that are introduced in this section. So namely here, if f prime of x is 0 for all x, and again, we kind of saw that statement here in this example, so that means it's continuous and differentiable, so mean value theorem applies. In a comma b, open, then f is constant. Now this should make a lot of sense intuitively because we saw that if its derivative is 0 for all values of x, then that means it's horizontal tangent line. It has a horizontal tangent line for all those values, and that means it must be a horizontal line itself, so it must be a constant. But how you can prove this by mean value theorem is you can actually pick any x values in between a and b. So namely you can choose, I guess, x and x1, how would I say this? I guess you can say x1 and x2 that are in the interval a to b. So namely we're going to kind of be looking at, so we're going to be considering the closed interval x1, f1, or x1, x2 I should say. And my mean value theorem, and I'll use the non-fraction version so I don't spend too much space here, is going to say that f of x2 minus f of x1 is equal to f prime of c times x2 minus x1. Okay? But since f prime of c is 0, because f of x is 0 for all values of x, and c is just some value in between these two, So we're just basically picking x values in between a and b, kind of to make a closed interval so that we can apply mean value theorem. Otherwise, we don't have actual existence on the endpoint possibly, just because it's open. But anyways, we can certainly do this. And again, this is equal to 0, which actually implies, if you think about it, the difference of these two f values is 0, so that means they must be the same value. Namely, f of x1 is equal to f of x2. And this was true, again, for any, so I'm just, I guess, adding f of x1 to the other side, but I wrote it the other way around, which is fine. So again, what this tells us is that for any x1 and x2 values you pick in the interval, the y values that they correspond to must be the same, implying that it's constant throughout. So they'll give you the same value. So this implies that f of x is constant, which I'm not going to write as a result. That's kind of straightforward after that. So I'll just put a tombstone there to complete the proof. In fact, now I'm pretty confident writing proof here. This argument is pretty solid. It's very straightforward. And in fact, this corollary, if you don't know what corollary means, it just means it's a consequence of a theorem. So it's kind of a follow-up of this. This is super straightforward. So it says if f prime is equal to g prime for all x in an interval a to b, then f minus g is constant on that interval. Namely, you can write one of them as a constant plus another, plus the other one. So in this case, f of x is equal to g of x plus some constant c. And how we can prove this, if you wanted to, which I'm not going to write, but I'll just explain verbally, is if you subtract these to one side, this is f minus g all prime. Because f prime minus g prime, by, I guess there's like a subtraction rule for derivatives. We know that, right? We know that if you take the derivative of a difference, it's the difference of the derivatives. So if you subtract this, you get f prime of x minus g prime of x is 0. And that kind of satisfies this, because f prime of x minus g prime of x is the derivative of the function f of x minus g of x. So we're kind of calling a function the difference of two functions, and it satisfies this. Its derivative is 0 because their derivatives are equal. So it's a little hard to say in words again, but we're setting f minus g of x, or f of x minus g of x, equal to some kind of greater function, so to speak. So its derivative will be the difference of these derivatives, and since these derivatives are the same, then the derivative of that greater function, of the difference function, would be 0. So this theorem is satisfied, so that means that function must be constant, but since that function is just the difference between f and g, then f of g is constant on the interval. And since f of x minus g of x is constant, just add g of x to the other side and you get this. So it's pretty straightforward. I don't want to get into the proof of this. But now we'll see some consequences of this, and then I want to do one more example of mean value theorem after that. Alright, so these are the last 3 examples we're going to see in this section. This last example here is really the one I wanted to show you because I think it's really fun and really cool. This first example, though, is a consequence of the theorem and corollary we saw, so it's a good application of that. And this one is, it's a kind of a, not technicality, but it's something that will kind of allow us to look back at what Rolle's theorem really says and to try to develop an understanding of some details there. In fact, it's kind of seemed to trick you, but not really. So let's take a look, obviously in order here. So we want to show that hyperbolic tangent inverse minus cotangent hyperbolic inverse is constant. Yikes. So that's a callback, obviously, to chapter 3.11. And in that, we must recall from, so let's do this. Recall, and this is again from 3.11. So I'll just write that here from chapter 3.11, that these derivatives, so let me write d over dx. So d over dx of tangent inverse hyperbolic inverse was equal to 1 minus x squared, 1 over 1 minus x squared. We actually proved that in the video for chapter 11. And we also proved that this is the same as the derivative of cotangent hyperbolic. So it's nice that we actually look back at this, because I even mentioned in that video when we went over this, over those derivatives, I thought to myself, and I said it out loud, it's quite striking to me that their derivatives are the same, and maybe that implies their difference is a constant, and I even said that. And that's the case actually because of these theorems, mainly from the corollary. Because notice here, if you let f of x be this guy, and g of x be this one, then by corollary, let me just write COR for corollary, well, f prime of x is equal to g prime of x for all x. So this implies that f minus g is a constant. Awesome. Do we want to find out what the constant is? We can actually do that by plugging in any value for x. The only problem, I think, is that I actually haven't, I didn't really show what these were. I want to do it, but we don't have space. So for this next example, we're letting f of x equal 1 minus x to the 2/3. We want to show that f of negative 1 is equal to f of 1, but there actually doesn't exist a number in between them such that derivative of that number is 0. So there is no such c. So that kind of falsifies Rolle's theorem, doesn't it? Kind of. Well, not really, actually. So the follow-up question here is to explain why this does not actually falsify or contradict Rolle's theorem. So first we need to show that this is indeed the case. And notice that f of negative 1 is going to be, well, when you plug in negative 1, you get negative 1 to the 2/3. Negative 1 to the 2 is positive 1, and then that to the 1/3 is going to be 1. So this is 1 minus 1, which is actually 0. And f of 1, similarly, is also 1 minus 1, which is 0, because, well, 1 to the 2/3 is 1, and 1 minus 1 is 0. In fact, this works for any even power. This really isn't technically an even power, though, but the numerator certainly is even in the exponent. And in fact, that part right there kind of tells you what's really going on. But if you take the derivative of this, so derivative of f of x is f prime of x. Notice 1 goes to 0, this goes to negative 2/3 to the x, well, x to the negative 1/3. Now this is the problem, because here we have an exponent that's negative now, and in fact notice that this actually has a vertical asymptote at x equals 0. So let me write that has a vertical asymptote VA at x equals 0. And notice x equals 0 is actually, x equals 0 is in the interval negative 1 to 1. And as it turns out, well, from negative 1 to 0, this function is actually, let's see, is it increasing or decreasing? I guess it would be increasing. And then from 0 to 1, it would be decreasing. So what that kind of tells us, and you can see that by graphing, basically what that tells you is that there's no dipping below or rising up like this. So there's no dips and no bumps, or whatever you want to call them, meaning that there's no point in between that will yield a horizontal tangent line. And this is really the part that contradicts Rolle's theorem, or that doesn't really contradict Rolle's theorem. So remember, in order to use Rolle's theorem, we have these 3 requirements. It has to be continuous, which the function is. The original f of x is, because there's no denominator and there's no even index radical. The radical here technically is the cube root, because the denominator and the exponent is 3. So actually this is continuous everywhere. But, we have these 2, which is the third requirement for Rolle's theorem. But the second requirement is not met. The second requirement is that it's differentiable on this interval negative 1 to 1. And it is differentiable. You can take its derivative, but its derivative doesn't exist at 0. So in fact, this tells you that it's not actually differentiable for all values negative 1 to 1. And that's what you need. You need it to be continuous and smooth throughout, which it's continuous throughout, but it's not smooth throughout. So there's kind of like this either sharp edge at some point or a point missing. In fact, really it's a sharp edge. So I'm not going to actually graph it, but I'll just kind of explain that the graph looks something like this from negative 1 to 1. So notice the y-axis is in between here. And it will do something like, maybe we can actually see what it looks like, because it gives you 0, and then when you plug in something in between, like when you plug in 0, you get 1. So it should look something kind of like this. So notice what this actually implies is that there's this kind of sharp edge at 0, so it's not differentiable there. Because to be differentiable means you basically have no sharp edges and you're continuously smooth everywhere. But really it means your derivative exists everywhere. And when you take the derivative, you find out it doesn't actually exist for some point in the interval. So this is the explanation why it doesn't contradict Rolle's theorem, which again is kind of technical, but it helps in our understanding of what Rolle's theorem requirements actually do for us and why they're necessary. Now, for this next example, we want to apply the mean value theorem to this function on this interval to show that we have this inequality met. Just for space, I'm going to erase this, lift this up, and then continue. Alright, so to begin this problem, let's first find the derivative of this, and let's consider mean value theorem. Now, of course, this is x to the 1/5, so this is continuous and differentiable on all values in between here. Notice its derivative, like with the previous problem, gives you a negative exponent. But actually, just to show you, because we need to find it anyways, derivative of f of x is 1/5x to the negative 4/5 after taking a 1 away from the power 1/5. And you may think, okay, we have a negative exponent, so that implies there's a 0 in the denominator, like we saw with the previous example. But that doesn't actually falsify mean value theorem in this case, because this is not differentiable when x is 0. In other words, the derivative only doesn't exist at x equals 0, but 0 is not in our interval. It was in the interval for the previous example, so that's where that fell apart. But here it's actually okay. So now, applying mean value theorem, let's see what happens. So mean value theorem says that there exists a c such that f prime of c is equal to, let's see, it's going to be f of 32, well, I guess it's b minus a, so it's going to be f of 33 minus f of 32 all over 33 minus 32. So I'm just kind of following my nose here. I don't really know where this inequality is going to come from, but we can try to figure this out together. Notice f prime of c is just this, where x is equal to c, so it's 1/5 c to the negative 4/5. So that's going to be fun. But notice this is equal to, well, let's see, that's going to be the 5th root of 33, because f of x is x to the 1/5, so that's 33 to the 1/5, which is just the 5th root of 33. Now, as it turns out, the 5th root of 32 is just 2, because 2 to the 5th is 32. The denominator is just 1, so I don't even need to write that actually, because all over 1 just is itself anyways. And now what? We want to show that this is somehow, this number here, is in between 2.5, or 2 and 2.0125. Geez, how do we go about that? Well, notice that this c value has to be in between, so let me just write, c is in the interval 32, in between 32 and 33. Okay, so notice this is going to be a positive value. So will that help us if we say that this is bigger than 0? I think so, because then we can add 2 to the other side. This means if c is in, let me write it like this, if c is in the interval 32 to 33, this means c is in between 32 and 33. Okay, so if we actually have that and make this the case, then we can find an upper bound for this guy here. And in fact, since the largest c can be is 33, then if we plug in 33, we get 1/5, 33 to the negative 4/5. But you know what? That's actually not the case. It's actually plugging in 32. And I know that sounds a little funny, but I know this will work because we're taking something to the 4/5. So that's the 5th root basically is the denominator being 5. And for 33, we don't know what the 5th root is, but for 32, we do know what it is, it's just 2. And this will actually work, but the reason why this inequality holds is because if you look at this part here, let me just write it down below. This is certainly true. If you take, actually no, we want to look at the other one. So we want to look at this. C is bigger than 32. Okay. In fact, maybe we can write it like it is over there. I know I'm kind of being a little sloppy about this, but it's okay. Everything's fine. So we have 32 is less than c. Good. We're going to take both sides to the negative 4/5 to get that power. Now notice, when you take both sides of an inequality to a negative power, something kind of funny happens. What happens is that this inequality symbol actually flips. And the reason why is because when you're taking two numbers that are both positive, which is clearly the case here, to a negative power, you're reciprocating them. So think of something like, I don't know, 4 is less than 6. If you take both of them to a negative power, In fact, it doesn't have to be -1, it could be negative whatever. This, again, just reciprocates these, and we get 1/4 and 1/6. And notice clearly 1/4 is actually bigger than 1/6. So reciprocating both sides of an inequality, if they're both positive values, flips the inequality. If one's positive and one's negative, the positive one will always be larger regardless. But if they're both positive, the inequality flips when you reciprocate. So this inequality symbol will flip, so we indeed have this actually. Perfect. So now, all we need to do is simplify this thing, and we're good to go. And I'm going to simplify it rather quickly. Notice 32 to the 1/5 is equal to 2. And this to the 4th is the same as 32 to the 4/5, and that's a 16. So that means 32 to the -4/5 then is equal to 1/16, the reciprocal of that because of the negative power. And if you multiply this by 1/5, you get 1/5 of this. And I'm going to write this in kind of a funny way. Well, not really. This is just 1/80. But notice this is, I'll write this in a funny way. So 1/80 is 1/10 of 1/8. I know 1/8 is half of 1/4, and I know 1/4 is 0.25. So as a decimal, this is 1/10 of half of 0.25, which is 0.125. And then when you obviously divide that by 10, you move the decimal over once to the left. So this left-hand side here really is just 0.025. 0.0125 is what I meant to say. There we go. So now let's clean that part up here. Right, so now finally, what we have shown is this side here is actually equal to 0.0125. That's greater than the 5th root of 33 minus 2, and that's greater than 0. Really, we should have it flip the other way around for this, but that's okay. We'll see that they're the same anyways. And now finally, adding 2 to all three sides of the inequality gives us indeed our result. So it's going to be, in fact, maybe we don't have to flip it. It's quite literally just this. So that actually satisfies what we wanted to show. So nice. It was a nice application of the mean value theorem. It was a little weird of an application, but it still works. And like I said, a lot of these applications and problems that involve mean value theorem or even Rolle's theorem are a little particular, but at least we can see that it is indeed a theme. Now, I said we would have time to show that that constant of the difference between hyperbolic tangent inverse and hyperbolic cotangent inverse. So let's take a look at that right now. All right, so we have a little bit of a problem. As it turns out, tangent hyperbolic inverse and cotangent hyperbolic inverse have complement domains, meaning anything you try to plug into one cannot be plugged into the other. So there's no value we can plug into both of them to actually see that they have a difference that's constant. So in fact, f minus g doesn't really exist. It's not actually a function. Its domain would be basically empty. So that's a kind of weird scenario that doesn't really contradict the previous theorem, because that theorem implies that f minus g is existent, but in this case it so happens that f minus g is non-existent, which is kind of bizarre. Basically, you can plug in one number into both of them. So this is kind of showing that here. I recall what the hyperbolic definitions are for those functions. And here I've actually just written out the explicit expressions for the inverses of tangent hyperbolic and cotangent hyperbolic. And you can see that no matter what you plug into x here to make this positive, because you can only have a positive inside of ln, since the denominator has a different swap here, this is going to be negative if you plug in that same x value, and you can have a negative inside of ln. So they indeed have complement domains, which again means that if you plug something into one, it cannot be plugged into the other. Okay. So now instead, we're going to do this. We're going to show that this crazy identity holds. And the way we're going to do that is we're going to let this guy here be f of x, and this guy here be g of x. We're going to show that f of x and g of x have the same derivative, and that implies that f minus g is constant. And then we'll plug something into f and to g, and we'll show that their difference will be negative pi over 2. And we're going to plug in any x value, but that'll be true for any x value you pick actually. It'll always be negative pi over 2. Because of the theorem we saw that f minus g would be constant if f of x and g of x indeed have the same derivative. So the first thing I'm going to do is take derivative of f. It's going to be a little bit of a journey, but it's not too bad. So we first have to recall that derivative of sine inverse is 1 over the square root of 1 minus the inside squared. So it's going to be 1 minus this fraction squared. And I'll clean all of this up in due time. Times derivative of the inside. Using quotient rule, we get all over the bottom squared. The numerator from quotient rule will be derivative of the top, which is 1, times regular of the bottom, minus regular of the top, times derivative of the bottom. So really this is just x plus 1 minus x minus 1. If you distribute the negative, you get negative x plus 1. So these cancel out, and we just get 2 on top. Great. Awesome. So that actually doesn't simplify too bad. Now the radical part we need to clean up a bit. I'm going to notice that if we have this radical, and I'll write it a little bigger here. Notice this is x minus 1 squared over x plus 1 squared. And if you multiply top and bottom by x plus 1, you can bring that inside of the radical as an x plus 1 squared. Because square root of x plus 1 squared is x plus 1. Well, it's absolute value of that, but when you bring it inside the radical, that the opposite is actually true. So again, we're going to distribute that into each of these two terms. Into this term, they cancel out. Into this term times 1 just gives you that quantity alone. Okay? So notice we just get x plus 1 squared minus x minus 1 squared. If you expand these out, x plus 1 squared is x squared plus 2x plus 1. Minus, if you expand x minus 1 all squared out, you get x squared minus 2x plus 1. And notice since we're subtracting, the x squares and the 1's cancel out. And 2x minus negative 2x is just 2x plus 2x, which is 4x. Fantastic. So this whole weird radical part actually just, believe it or not, simplifies to the following. It simplifies to 4x in the denominator, and then inside the radical, and then we have x plus 1 on top. So this is going to be x plus 1 on top, the square root of 4x, and then we have times 2 over x plus 1 quantity squared. And this even simplifies more, as you can tell, because notice the square root of 4 is actually 2, so we can bring this 4 out as a 2 outside of the radical. That cancels this 2, and this x plus 1 cancels with one of the powers here. So really it's just going to be 1 over radical x times x plus 1. So let me write that as our final result here for the derivative of the first guy, f. 1 over the square root of x times the quantity x plus 1. Let me write the x plus 1 in front. Just like that. Awesome. So it's 1 over x plus 1 in parentheses times radical x in the bottom. Let me erase some of this and let's find the derivative of g. So derivative of g is actually a little more straightforward. Recall that derivative of tangent is going to be 1 over 1 plus the inside squared. Since it's 2, we'll have 2 over 1 plus the inside squared. So that's radical x squared. Notice radical x squared is just x. Okay? Times, by chain rule, derivative of the inside. Kind of like here we had the quotient rule, which was derivative from the inside from chain rule. Derivative of radical x is 1 over 2 radical x. Because remember, radical x is x to the 1/2. Its derivative is 1/2 x to the negative 1/2, which is just this. These cancel, and we indeed get this same exact thing. Only it's a lot more simpler, and we don't have to do this crazy simplification to see that. So we can see that their derivatives are the same. That means their difference must be constant. So we can plug any number into each of them, and they should give you the same value. So I'm going to plug something into into f and into g, the same number. Again, that didn't work for our hyperbolic friends, which is unfortunate, but here it should work for the non-hyperbolic ones. So into f, what can we plug in? Well, I guess we can plug in 0. Yeah, 0 works. You can plug 0 into both. So when you plug 0 into f, you actually get sine inverse of, again, negative 1 on top, positive 1 on the bottom, so that's sine inverse of negative 1. So when is sine negative 1? Sine is negative 1 at negative pi over 2. Okay, and what is g of 0? Well, g of 0, notice, is just 2 times tangent inverse of radical 0. For radical 0 is just 0, and tangent inverse of 0 is 0. 0 times 2 is 0. So g of 0 is actually 0. So notice f minus g is going to be, well, this. It's going to be negative pi over 2. So that means f of g, or f minus g, f of x minus g of x, is equal to negative pi over 2. Now you may say, well, that's only for x equals 0, but no. We prove that the derivatives are the same, meaning that their difference is always constant. We just picked a particular value 0 to plug in to see what that number is. So I plugged in 0 because it was nice. When you plug in 0, you get the same value, obviously. But no matter what number you pick, you can try your own if you want. You'll get negative pi over 2 as well. And then notice just adding g of x to the other side gives us our identity. And we are done finally. That's all I wanted to say for 4.2. And again, there was a lot of variation going on here. 4.3 is a little more specific. We'll actually be connecting calculus finally to the shape of a graph of a curve. That's going to be really, really nice, and that has a lot of direct applications. This was a little bit of an oddball, I'll admit, but it was still good to see, and I'm glad we saw it. So I'll see you in the next video for 4.3. It's going to be a lot of fun. Hope you enjoyed this, and I'll see you then.